picture, right? Because all these are related. Delta H of desorption is a constant for a particular reaction, of course. And what is changing here is the Tp. So it means that your maximum desorption temperature does not, in this case, does not depend on the initial surface coverage, where for first order reaction, whereas for second order reaction, your maximum desorption temperature does depend on your initial coverage. So let me, if you somehow measure your desorption rate, right, and you change and not different initial surface coverage. So the typical picture you have is that you have the vacuum chamber. You expose the gas on your surface, right, on your surface, and the surface absorbs certain part of this gas, and that is the defined N naught, because that defines the initial absorption surface coverage you have. And this exposure is often measured in terms of Langmuir. Okay, so that this is a good way to honor Langmuir. So when you expose a gas, so exposure is often measured in terms of the unit of Langmuir. And Langmuir is 1 times 10 to the minus 6 torr second. Okay, so I think we talked a little bit about that when we at the beginning of the course that we talked about this exposure. And the unit Langmuir is 1 times 10 to the minus 6 Langmuir. And the reason why we use this unit is because for a sticking coefficient of 1, right? Remember when we're talking about sticking coefficient of 1, at this pressure, at 1 second, you would have a monolayer coverage, and that's the physical meaning of a Langmuir. So that's why it's kind of nice to do that. And so N naught really is surface coverage measured in terms of Langmuir, okay? And you have different, different curve here correspond to different N naught initial condition. If you do your experiment with different initial surface exposure and plot and measure your rate of change, right, your desorption rate for that experiment, you can discover your order of the desorption quickly, because if your peak all occur at the same temperature, maximum temperature, you would have the first order reaction, because according to this, it does not depend on the initial coverage. But if your rate, if your temperature, maximum desorption temperature is actually going down, then you know right away that you have a second order desorption. So it's a very powerful, this so-called red hat analysis is a very powerful idea that immediately tell you the order of desorption that you have. Okay, and so you can see right away, you just plot it out, it's moving this way, you know that you have a second order desorption. And there are a couple other things of interest here, that this peak is actually, if you look closely into the shape of your curve, people find that, okay, for first order desorption, you have an asymmetric line shape of this curve, whereas for second order, you have a symmetric. This is the totally Gaussian-like type peak. And the same peak temperature, P stands for peak temperature, as the coverage is increased, whereas here you have desorption decreasing Tp as the coverage is increased. Okay? And oftentimes, people carry one step forward, which I think, in my personal view and experience, is that this is a little bit too much. Extending the red hat equation a little bit too far. And what do people do normally? Well, they saw this, and then they proceeded to try to deduce the absorption energy, so-called activation energy, desorption energy, delta H desorption. And by analogy, they would then say, okay, if we equate the desorption energy to the absorption energy, I should be able to tell me something about the interaction But I think this is a little bit too far because they usually use this type of expression, which is an offspring from this type of equation. But there's a couple of problems with this type of analysis that you try to equate your desorption energy to TP, for example. And the maximum desorption rate, RDP, is the desorption rate at the peak, okay? Because you have N naught and so forth, but in the case of first order, this epsilon here actually depends on the flux, the coverage. The N is the coverage at the peak maximum, okay? And sometimes this flux this flux depends. This desorption rate is depending on the flux itself. So it's an interrelation, and this could be temperature dependent. This flux could be temperature dependent. So here we are assuming this flux, right? This surface coverage does not depend on temperature, which is certainly not true. And so if you carry this out, your activation energy will be incorrect. But some people do carry this out, and sometimes when you read the literature before 1980, a lot of crap numbers show up, right? People see this, and then they did something, and they come up with a number like for this, and usually they are wrong. So when you read literature, you have to be careful about if people say they can find the desorption enthalpy, you have to take it with a grain of salt. The other problem with this type of thing is that you really have to know what is your P exponential factor, mu1 and mu2. And those are not easy to find. And when you do this calculation, oftentimes people just assume mu1 to be 10 to the 13 or something like that. Some crazy number that they come up with. And usually it's not so accurate for the reaction of interest. Okay? But the upshot of all that is that I just want you to recognize the shape when you are looking at the desorption rate, and then you have to remember it may be possible to deduce the enthalpy, heat of enthalpy change, or the activation energy of the desorption. Okay, so that's all I want to get out from this shape. Okay. So. That's it, and so what do you see on here? Let me go back to my main notes here. So there's a quick rundown on some picture that we got. If you look at this TBD and you assume a linear heating rate, then you will see peak like this. You see peak like this. Here is a change in the desorption temperature, or the heating of the desorption rate, essentially R sub D. But sometimes people measure the total pressure. Okay, so of course when you heat it up, the total pressure will increase continuously, and it will steady out, right, as you continuously heat up. And sometimes you heat it up very fast, and by fast you mean that half a second. Okay, half a second. So if you have some instrument that you can measure pressure change to that kind of speed, then you are in the so-called fast desorption condition. You just send a heating pulse, extremely fast heating pulse to your sample, and then you quickly measure the total absorption that you see, and you will see something like this. And this heating pulse is usually half a second, less than half a second, certainly less than a second. You can see that it's measured in terms of milliseconds. And you see a quick rise in the total pressure, in the pressure or partial pressure or whatever gas that you're interested in. And if you take the derivative of this, right, it will correspond to a normal rate, a slow heating rate that people normally do in TBD, that you have a linear heating rate like this. And this exactly corresponds to different temperature, desorption temperature you find. People don't